And hello, welcome back. So last video we actually spent some time to try and guess what our temperature and velocity profiles are. Okay, in Bijon's textbook they just put this exponential curves here. Okay, one based on the momentum boundary layer thickness, and the other one based on the thermal boundary layer thickness. And the velocity is based on both of these boundary layer thickness, whereas the temperature boundary profile is actually based on the thermal boundary layer thickness, and of course x. It's exponentially decreasing, which sort of fits, at least some preliminary analysis of our equations just by inspection and thinking out loud, that kind of thing. So the logic was explained in the last video. So now that we have that, we are ready to start our integral solution. Okay, so anyway, some qualitative explanations being done here. Okay, so now for integral solutions, we take the dimensional form of the momentum, energy, and what do you call that? Continuity equation. We integrate it across the whole boundary layer. So in this case, the boundary layer will be in the x direction, no longer in the y direction. So we'll integrate across x. So effectively, we'll just be integrating, as you see here. I have this equation here, the momentum equation, the boundary layer equation, and then I'll just integrate it across x. So we integrate it to the point where where we have all our free stream conditions. So u equals to u infinity, which is equal to 0, v equals to v infinity, which is also equals to 0, t equals to t infinity, which is the free stream temperature. We can do the same thing for the energy equation here. Okay, we integrate with respect to x. I just put the dx in front because it's easier to copy and paste. And in you won't find this nomenclature often. But basically, what I'm saying here is just to say integrate this whole term with respect to dx. Okay, and that also helps you to always to remember to write your dx. Yeah, so we just write it in front first. Okay, and anyway, with if we talk about products, commutative law applies, so we can just swap the positions. But it may not look as familiar, but okay, that's just a stylistic choice. Okay, remember with all our when we are integrating, remember with all our properties like this expansion coefficient, momentum diffusivity, thermal diffusivity, all of these are evaluated at some average value. We call this average temperature the film temperature, which is Ts plus T infinity over 2, just the average of them. Okay, so let's see how we can start manipulating our equations. So we do it very similar to our forced convection. Okay, this is our continuity equation terms. Okay, so alright. Where do we start? Okay. So for the energy equation, we over here, this is our energy equation. I'm not going to start integrating it straight away, but as is customary with our what do you call that? Energy equations. All right. It's customary with our energy equation in our boundary layer integral solution. Somehow, for some reason, we like to combine the terms because it will make it easier to integrate later on. Okay, so you don't want to integrate u del t del x. You rather integrate ut, del by del x of ut, del by del y of vt. Okay, because you won't need to think about product rule and everything like that. So we make life easier for ourselves. Okay, so so I'm going to use product rule to say that u dt dx, u dt dx equals to dut dx minus t du dx, and I'll do the same for the y advection terms. So that's why we had this thing over here. This is basically just a product rule thing. Not going to explain too much. One thing I want you to note is that dv dy plus du dx equals to 0. Why? Because continuity equation. Okay. Fortunately, we can use the continuity equation to say that all these terms will just drop out. Okay. So before integrating, we want to make life easier for ourselves. Okay, so these terms will drop out, and then we'll have this. And now we are ready to integrate. Okay, so let's do this. We will just like I said, copy and pasting is easier with this, putting the dx in front. So 1, and this one should go at the bottom here. Oh dear, I think I need to just compile first. Okay. Let me copy this integral operator throughout, and I'll just quickly do this. Okay, so at least this advection term is now easier to deal with. So what do we do? We need to have ut evaluated at what? Okay, the free stream. So I'll just put infinity minus ut at 0. Okay, so that's the first term. Okay, fortunately, both of these terms actually drop off because u equals to 0 at both the free stream and the wall. So this term drops to 0, thankfully. For the second term, we actually have to use Leibniz's rule, so we'll just skip that for the time being. Okay. For this term, the rightmost term here, I will just bring alpha out, and we'll just basically need to evaluate. Okay, we have dt dx, right? Okay, we'll have dt dx. Okay. Firstly, evaluated at the free stream minus dt dx at the wall. So at least this part becomes a little bit easier. So we have a wall heat flux here, dt dx at infinity. Well, at the free stream, the temperature is infinity, T infinity everywhere, so we won't have very much heat flux. We can just drop that off in comparison to the heat flux at the wall. Okay, because this term is small in comparison with the wall heat flux, I can just drop this thing off. Okay. Okay, so now yeah, fortunately or unfortunately, we'll have to use Leibniz's rule to deal with this term. Let me check the time. Okay, so yeah, we'll need to use Leibniz's rule. Okay, Leibniz rule is like that. Okay, so if let's say we have d by dx of blah blah blah. Okay, and fx of y, this will be equals to fxy evaluated at y2 equals to bx, and d by dx of bx, okay, minus fx of y blah 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 evaluated at y equals to ax, where ax is here, and then d by dx of ax plus this integral will be on the outside, then you just swap the integral and the derivative part. I'm not going to go through that. I already gone through that in a few videos prior when I was talking about forced convection. Okay, so what are we going to do now? We'll need to first thing first, well, our x and y's are kind of swapped around. Okay, note that our x and y is swapped around. So everywhere I need to, there's an x, I need to swap it with a y. Everywhere there's a y, I need to swap it with an x. Okay? Just by nature of the coordinate systems. Okay, so the d by dx will become d by dy. Then instead of substituting at x1 and y1 and y2, I'll substitute at x1 and x2. Okay, I will still have a fx and y. Instead, of course, I can just swap it around for consistency. And okay, we are pretty much more or less done with the first term, the leftmost term. And then I'll just swap the x and y here. A little bit tedious. So yxy, and then d by dy, b of y. Okay, this one will be y, x, y. X will become y, y will become x. And let's compare. Okay, y x equals to by d by dy by minus f y x equals to ay d by dy of ay. And then the last term I'll need to change it as well. So I'm going to change y1 from y1 to x1 and y2 to x2. Then I'll do a partial by partial y x dx. So I just reversed. Everywhere I see the y, I will replace it with x. Everywhere I see x, I'll just replace it with y. So that's to make it more consistent with what we are doing here. So we can do this. Integrate from 0 to x infinity, wherever the free stream is. It could be the boundary layer, thickness, or whatever. Okay. D vt dy, dvt dy. Okay. So let's do that. Let's do some substitutions now. What is a of x or a of y now? Okay, x1 equals to 0. So x1 equals to 0. So wherever we see a of y, and that equals just to 0. So that's one way we can swap. One thing we need to swap out. Okay, maybe I'll just do a comment of that first, because it's like in the way. So let's do the x2 part. x2 equals to, well, the free stream. Where's the, for high Prandtl number fluid, we just call the free stream delta P. Okay, which is the momentum thickness. Okay, x2 is the momentum thickness, and this will actually be a function of y. So by equals to delta P. Okay, in delta P, the momentum boundary layer thickness. Okay, in the momentum boundary layer thickness, we will have T equals to T infinity, V equals to V infinity, which is what we actually set up with to do. Okay, so what is f, x, and y? Or f, y, x? That is simply just V and T. Okay. So we substitute all this back. Okay, and then into Leibniz rule. Leibniz rule. Okay, so everywhere I see, oops. Yeah, I think I copied the wrong one, the wrong Leibniz rule. Okay, that's better. Okay, so x2 equals to what? x2 equals to delta p, right? So b is actually delta p, and x1 equals to 0. That makes it easy. fyx equals to vt. Okay, so we will actually have vt evaluated at b of y. So this is vt evaluated at b of y, which is the boundary layer. Okay, then you'll have this d by dt of this boundary layer thickness with respect to y. Okay. Next thing is we will have Vt at x equals to 0, which technically should just be 0. So we can just drop this whole term off. Okay. And then the last term, very simply, okay. Alright, so hopefully that actually shows you how things should be done. And if we were to just simplify this whole thing, we'll drop off the term that is just 0. Okay. All right. Now, and it's a good thing. Okay, it's a good thing that this so-called what do you call that? Yeah, it's a good thing that this so-called boundary layer. Okay. When we evaluate at this boundary layer, right? Okay, v equals to 0. Okay, so again, when we are at the boundary layer thickness, this term actually becomes very small because it's the product of v and t. This v will become 0 at the velocity boundary layer or momentum boundary layer. So actually this term here will also drop out, thankfully. Okay, normally we cannot just switch the integration and differentiation parts. Okay. Now let me put the reasoning why we can just take that off. V equals to 0 at delta p. Okay. That's why. Okay. It pretty much just reduces to 0. Okay, so now we just realize we can just swap these things around. And one more thing, I actually want to change some variables to make it easier to non-dimensionalize. conventionalize. Okay. Because we know we are not actually interested in the absolute temperature, we are interested in the value of the temperature minus the fluid temperature, the relative, and that's just convention, you know. So I want this side to be t minus t infinity, okay, t minus t infinity rather than just t, right? Okay, so we can do that, okay, because dt, okay, dt and t minus t infinity, dt and dt minus t infinity, they are basically the same. Okay, so we can just pop in an extra term here without worrying. Okay, same reason. I mean, we can actually what do you call that? We can actually do this over here, t minus t infinity over here. Okay, we can do this t minus t infinity over here, and then if we just substitute t minus t infinity here, then all the way through we'll be using, wherever we see t over here, we'll have t minus t infinity. Okay, one more time. If we wanted, okay, we can actually substitute t over here, dt dx, dt dy for t minus t infinity. Okay, and all the way through, wherever you see t, you can have t minus t infinity. So this thing is kind of a legal move, okay, so to speak, a legal move. And basically what we are left with on the right, the left hand side, t minus t infinity, and this is the standard form of the boundary layer equations that you will see in the textbook. Okay, you will have this form over here. So okay, just to really drive the point across, I will just put the third equal sign here. Okay, I'll just put the third equal sign here. It is totally legal to do that. Okay, hopefully you understand why. But once we have this, we are able to substitute all of this back here. Okay, subs back in energy equation. Okay, so instead of this, I will use the momentum boundary layer thickness directly. I'm not going to so-called use this x infinity anymore. Okay, and just to make things neater, let me remove the x1 and x2. And again, delta py, and of course I will change over the minus signs. T infinity minus t, I'll get rid of the minus signs here. And basically we're done. Ta-da! Okay, let me remove the brackets just for sake of neatness, and just make the thing clear. Y equals to 0, or x equals to 0. Yeah. There you go. This is the first of our integral solution, the integrated form of the boundary layer equation. This is the energy equation. Okay. Okay, so next. Okay, we don't have time anymore. I'll just stop now. I'll do the next video where we'll just take a look at the momentum equation. You look at the momentum equation. Okay, so yeah, I'll stop here. Thanks for watching.